Today we're shifting gears and we're going to be looking at lenses. And lenses also apply to the lens mirror formula, so we can mathematically calculate where our images are going to be and where our height is going to be. However, there are a couple of different rules, and there's a few tricky things with lenses, because with mirrors, as these two are being mirrors over here, the light will reflect off of those mirrors. However, with lenses, the light is going to be going through those lenses. So we're going to do a quick review of concave and convex lenses. So we first started off with the concave lens, and when parallel rays come into this, we can see that, let me get a little closer, we can see that they are going to converge at the focal point. So if you see over here, that all of these light rays are going to be converging. And where they converge right here at this point right here, this is going to be the focal point. Again, parallel rays coming in are going to converge at the focal point. If I go to the convex mirror, here's the convex mirror. Remember, concave goes in and convex is bulging outward towards the light source. So you can see that these rays are going to be never converging on the same side of the mirror. They'll actually converge as sightlines on the opposite side of the mirror. So now we're going to be switching to lenses. And if you have a lens like this, which is very, very flat, what's going to happen is your light rays are simply just going to go through straight. So now we have these two lenses that are curved. This is a convex lens, and this is a concave lens. We're going to be primarily focusing on the convex lens, and a lot of people try to call this the concave lens, but if you remember, caving goes in, like caving in, convex bulges out. So let's take a look first at the convex lens. What we see here is when we put this in front of the light rays, parallel rays of light that are coming in are going to converge right here, and this is going to be the focal point. With the concave lenses, it's going to be spreading outward like this. So what's going to happen is, as these diverge, you can trace these backwards, and you can even see there's a slight reflection right here. This is going to be the focal point on this side of the lens. However, there's going to be a focal point on this side of the lens, and there's also going to be a focal point on the other side of the lens. With lenses, there are actually two focal points. So those are some of the points we'll be looking at for today. We'll get the lights back on again. And the light box off, and we'll readjust this so you guys can see. So this is section 18.2. So you guys are going to need your ruler for this as we draw a couple of these lenses. Let's first start off with the convex lens, the one we're going to be doing most here. So we can do curvature like this and a curvature like this. So this is the convex lens. And over here, if we can do the concave lens by showing the curvature like this. This is the concave lens. So what we're going to do is we're going to follow some of these light rays, and we're going to follow a light ray going right through the middle of this. And if it's going right through the middle and right through the center of this lens, this light ray will continue on its path. There's not going to be any angle modification or change to this. So remember, with mirrors, it's just going to be reflecting off of the mirror, but now we're actually going through a different material like glass or plexiglass or acrylic. That will also affect the bending of this, because in the mirrors we're going to have reflection, but in the lenses we're going to have refraction. Okay, so let's go ahead and take a look at this right here, and we're going to see what happens when a light ray comes in up here. So when the light ray comes in up here, there's a curvature, and the normal actually is going to look like that, this is actually going to be the flat surface, so we'll just draw a solid line. Here's the solid line. It's meeting a curved surface, but on a minute scale, it's going to be a flat surface. So we're drawing this flat surface. We have multiple flat surfaces that are going to make this curvature right here. What I'd like you to do is I'd like you to draw now the normal to this, which is going to be perpendicular. So I'm going to do this with the dotted line. Okay, so there's my normal. The light's coming into this lens, but it's a curved lens, and we're imagining that at the point that it comes in, it's actually going to be flat. So here's the normal. So let's see what's going to happen to this. This is my angle of incidence coming in right here. So here's my angle of incidence. And if you remember, we're going to be going into a different material. What's going to happen is this is going to bend toward the normal. So we have to draw a smaller bending of this, smaller angle like this. So that's what my light ray is going to be doing. So it's going to be bending toward the normal. Now it's going to hit this surface over here. Let's go ahead and redraw our normal. Well, if it was exiting right here, the normal would be, or the surface would be straight up and down. So this surface is also a flat surface. We're going to draw a straight line like this. And let's draw the normal to this one. So the normal will look something like that. So here's our normal here, and there's our normal there. Again, the angle of incidence coming in, and the angle of refraction is going to be smaller, if you remember, because this is an optically denser material than the surrounding air. This beam of light then continues. It also hits this curvature, but it's a flat surface on a microscopic scale. And so this is going to be the flat surface, and here's the normal. So now what's going to happen is we're coming in. Let's extend this normal a little bit. Okay, we're coming in at a very, very small angle. What's going to happen to this? This is going to bend outward away from this normal. So our exiting angle is going to be larger. And it will meet at that point right there. And this will be the focal point for this lens. If you have another ray coming in here, it's going to bend inward, and that's going to bend inward even more toward that focal point. So this is called a converging lens, because the rays of light are going to be coming together. Let's see what happens with the concave lens, as we saw with the demonstration. So here comes my ray of light coming in. When it goes to the center, it's going to go directly straight through the center like this. But now we're going to see what happens to a ray of light coming in up here. So now we have this curvature, but it's actually a flat surface on a microscopic scale. So I'm going to draw what this flat surface would look like just at that point right there. And now what I'm going to do is I'm going to be drawing my normal to that line. So here is my normal. Let's extend that normal out a little bit more. Okay, so here's my angle of incidence coming in. Okay, so as it comes in, it's not going to continue at the same angle. It's going to bend toward the normal. We're entering a denser material, so it's going to bend towards the normal. So it's not going to go straight down this line. It's going to actually bend toward the normal. So it'll look something like that as it bends towards that normal. So now we have another flat surface on a microscopic scale. It's actually curved. Let's go ahead and draw our normal to this with a dotted line like that. So this is not going to continue on its straight path because it's entering an optically less dense material. So what's going to happen is it's going to bend away from the normal. So here's the path it would have taken. It's actually going to bend a little bit away like that. And here's the incoming ray. Here's it inside the lens, and this is going to be bending away. And you can see that these two rays will not converge. So this is called a diverging lens. There are also two factors that will affect the focal point. So we're going to discuss the two factors that will affect the focal point. Two factors for the focal point or the focal length. The first factor is going to be the curvature. The more that's bent, the more it's going to bring the focal point closer to the lens. The more flat that it is, the farther away the focal point is going to be. Another factor that will affect the this focal point is going to be the optical density. If you remember Snell's law, this is the index of refraction. So the more optically dense your material is, the more it's going to converge it or diverge it. The less optically dense it is and the closer it is to air, the more they're going to be going through straight. So those are the two factors that will affect your focal point for the lens. Now, there's rules to draw the lines as they go through the lens, and we're going to go over these rules. And let's go ahead and draw our lens. So if you can draw a line down here. Like this. And we're going to draw our lens in the middle. Okay, now you can do this and draw this lens, and this is going to be a convex lens, like this one right here. So we're going to be expecting the light rays to converge. So let's go ahead and put the focal point about 3 centimeters away. But actually, because this is a lens, there are 2 focal points, one on each side of the lens. So we have 2 focal points because light can pass through both directions. We can have the light coming from here to converge here, or the light coming here and to converge here. So the light passes in both directions. So let's go ahead and get an object. Let's say our object is, we'll just make it over here. And we'll just draw 2 lines up like that. We won't measure it. So here's my object. So the first rule is rays that come in parallel are going to do what? Now this is just like the mirror. They're going to exit through the focal point. If this was a mirror though, this would then reflect and go down through this point right here. So here's the focal point here, and here's the focal point here. And in lenses, the focal point for convex lenses, the focal point is going to be positive. So rays that come in parallel are going to exit through the focal point, like that. So that's rule number 1. So again, parallel rays exit through the focal point. And of course, since it's a lens, it's a focal point on the opposite side. Now, just like mirrors, rays that enter the focal point are going to exit parallel. So that's going to be rule number 2. So rays through the focal point exit parallel, just like the concave mirror. Extend this out a little bit more. There's a third rule, and rays that go through the center go on a straight path. And if you draw those and connect them, it should all meet at that same point right there. So we'll go ahead and we're going to draw a line. And what's going to happen is, for this case, we're going to have an inverted image. And it is going to be a real image. So we have a real inverted image. So forgot to do the third rule. So the third rule is rays through the center go straight. So what we're going to do is we're going to do a couple examples, and we're going to see what happens when we approach the focal point, and then we're also going to see what happens when we go on the inside of the focal point. Now, the symbol for convex lenses, if you follow the curvature right here, we're going to make a solid here and a solid line here, just to that point, and a solid line and a solid line here. So it sort of looks like an arrow up and an arrow down, and this is the symbol for our convex lens. So let's go on to the next page, because I'm running out of space. And what I'd like you to do is I'd like you to get 2 pens. I'm using a red pen and I'm using a black pen, because each of these drawings are going to have 2 colors on them. So what I'd like you to do is to draw your line. This is, again, your principal axis. And we're going to be drawing our lens through the middle like this. And we're going to indicate they are convex lenses and converging lenses with these symbols. So if you can, on this line, measure the focal point at 3 centimeters, but I'd also like you to do twice the focal point at 6 centimeters. So the focal point is equal to 3.0 centimeters. We'll also need them on the opposite side at 9 and 12 on my ruler, or 3 and 6 in the opposite direction. So here's your focal point here, and here's your focal point here. This is going to be twice the focal point and twice the focal point. For these lenses, your focal points are always going to be positive. Now let's draw an object. This object is going to be drawn outside of the 2 times the focal point. What I'd like you to do is I'd like you to make it 2 centimeters tall. So here is our object. Okay, here's the object here. And we're going to now follow the rules. Rays that come in parallel are going to exit through the focal point. Now, just because we have twice the focal point, don't have your rays exit through twice the focal point. We're still going through the 1 focal point. So you'll draw your picture like this. Let's go ahead and draw my rays that are going to be going through the focal point in front of the lens, like this. Rays that come in through the focal point are going to exit out parallel. And you can check to see, is it a good match? You can then match up your 3rd ray to the center. And where the 3 converge, this is where your image is going to appear. Okay, so here's your image. And this one is going to be, it's a real image just as before, and it's smaller. So it's a real and smaller image. It's also inverted. So it's real, inverted, and it's smaller. The reason why it's smaller is because we are outside twice the focal point. So now I want you to get your different color pen, and we're going to be seeing what happens exactly at twice the focal point. Okay, so we have this, and it's the same size. So here's the object at twice the focal point. Let's go ahead and draw your parallel rays, which is going to be very similar to the previous parallel rays coming into the lens. Coming in parallel, we are going to exit through the focal point. So it's going to follow the same path as that one right there. Okay, this is where it gets a little bit different. We're using the same rules, but we're at a different distance. Rays that go through the focal point are going to exit parallel. And then again, we can do our third point going through the center and see do those match up. It's close. And what's interesting is that these should converge at twice the focal point. It's a little bit off, but in theory, when your object is at twice the focal point, object at twice the focal point, what happens is your image is going to be at twice the focal point. But what's happened to the image? As we approach the focal point, it went from this size to this size. It started off as 2, this one's smaller. This one is actually larger. So this is also a real image because the actual light rays are converging. It's inverted. And it's larger. Well, it's larger than it was previously, but it's real inverted. It's the same size. So in this case, the height of the object equals the negative height of the image, because inverted means you're going to have a negative height. And since it occurs at twice the focal point, the distance of the object equals the distance of the image. Remember, both of these distances are going to be positives. Both of the focal points will be positives as well. So now what we're going to do is we're going to see what happens when we get closer and closer to the focal point. So let's go back to a drawing down below here. You can draw this same position like this. Here's the symbols to indicate it's a convex lens. And we need to put our focal points in the same places. So it needs to be at 3, and here's twice the focal point. Here's 3, here's twice the focal point. So let's choose a point right in between. And again, if you remember, the height of my object is going to be 2 centimeters. Let's go ahead and put this over here. Height of the object is 2.0 centimeters. So we're now going to be drawing our object with height of 2 centimeters. Does this still hold true? Is this like a mirror where the closer you get to a focal point, the larger the object will get? Here's the focal point, twice the focal point, twice the focal point. Can you guys draw this? I'd like you to get some practice doing this and following the 3 rules. So I'd like you to pause it now and come back after you've finished, and you can always change it. Hopefully you've drawn this. So I'm going to go through the steps again in case you need some more help. So again, this is a lens. My light is going to enter and not reflect. It's going to be coming into the lens. It's going to be exiting through the focal point. That's my first one. This one didn't draw my lens long enough for this. Let's go ahead and just extend that a little bit more for my sake. There we go. This is going to exit out parallel. Let's see, is that a good match? Is that right? My third confirming line is going to go through the center, and that's pretty close. So here's my image over here. So the closer you get to the focal point, the larger the image is going to be. So the closer object is to the focal point, the larger the image will be. Now, if you remember when we had a concave mirror, and when we hit the focal point, that's when our image is going to become inverted. And the same thing happens here. What I want to do is I want to show you, well, what happens when it's actually at the focal point? Okay, so let's draw our first line right here. And here's my object. That's the height of my object. It's still 2 centimeters. My first ray will be just like this original one right here. Objects that enter in parallel are going to exit through the focal point, like this. Okay, the second rule states that, well, rays that come in through the focal point, but I can't come through the focal point on this side because the object is at the focal point. So we have to actually rely upon the third rule, which is rays that are going to be going through the center are going to continue on straight. Rays that go through the center continue on straight. And you'll notice something interesting. I'm going to cover up this portion because it's sort of like an optical illusion. Do you notice something interesting about those lines? These lines are parallel. When will parallel lines converge? They will not converge. They will not converge on this side of the lens. We can't even draw sight lines backward because parallel lines on the other side will not converge either. So when the object is at the focal point, the rays exit parallel. And so they never converge. Well, what does it mean that they'll never converge? Well, since they never converge, they never form an image. That means your object is going to be invisible. So we're going to continue this process, and we're going to be moving more inside towards the lens. Now we're going to be going on the inside of the lens, and we're going to see what happens. Okay, so let's go ahead and draw, maybe create a little bit more space for this one, and you'll see why. And I'm going to be drawing my lens like this, kind of large too. And the focal length is going to be at 3.0 centimeters. The distance of the object is going to now be at 2.0 centimeters, and the height of the object is still 2.0 centimeters. So let's create our focal points, and in this case, we won't need twice the focal point. We're just going to do one of the focal points. So here's my focal point, and here is my focal point over here. Okay, let's put our object, at 2. Okay, there's the distance of my object, and the height of the object also is 2 centimeters. Okay, so here's my object. Okay, let's draw our 3 lines. the first line comes in parallel, exits through, hopefully you're saying right now, the focal point. Now this is a strange one because my ray of light cannot go through the lens if it goes through that point over there. However, we can align this top with the focal point there. Okay, so aligning this with the focal point, our ray of light will enter the lens over here, and when it's aligned up with the focal point here, it's going to exit out parallel, like so. Okay. So for this, we only have the two lines, but we can actually add a third line, because if you remember, what we have here is the rays that go through the center are going to continue on their path. Okay, so what is going to happen to all these lines? This one's going off this way, and these are going off this way. These aren't even parallel, they're diverging. Everything's diverging, meaning that these light rays will never converge. However, their sight lines can converge. So we trace backward from where they go through the lens. Okay, we trace back with our dotted sight lines. Here's this one. Here's this one. And then here is this one. Okay, and they should all converge near the same point. This one's a little difficult to draw. So we're going to show that our image is going to be way over here. So this is not a real image. When we are using forgot to add the symbols, a converging lens, and your object is on the inside of the focal point, we're going to get a virtual image because we used sight lines. It's a virtual image. It's larger, and it's not inverted over here. It's actually erect. Well, what functionality would this be to have your image appear larger on the same side of the object? Well, if you're looking from the other side, you can draw a giant eye like this. Here's your eyeball. Looking at your object through this concave lens, what are you going to see? You're going to see a larger image. What have you just created? You've just created a magnifying glass. That's the functionality of having an object on the inside of the focal point. So let's do some mathematics. We're going to be measuring to see where did our image occur. And for me, it's very, very close to 6. You can see it's about 6 centimeters away. So the distance of the image, according to my graph here, is 6.0 centimeters. However, it's actually on the same side as the object, so it's a negative. The height of the image is actually positive because it's an erect image. Let's go ahead and measure the height of this. And for me, I got about 5.7, we'll say. So 5.7 centimeters. Let's go ahead and calculate what the distance of the image should be based upon the lens mirror formula. So I'm going to show you that the lens mirror formula also applies to lenses. So remember, the inverse of the focal point is equal to the inverse of the distance of the image plus the distance of the inverse of the distance of the object. We have the focal point, we have the distance of the object, that's our starting point. We're trying to calculate this. So the inverse of the distance of the image will equal the inverse of the focal point minus the inverse of this. Just rearranging. You can get your calculators out. We can go ahead and now plug in the inverse of the focal point. 1 divided by 3 gives me 1/3 minus 1 divided by 2. Okay, when I do the inverse of this answer, I get -6. So the distance of the image is -6.0 centimeters. Pretty close to that. Let's go ahead and use the magnification, the hi-ho over di-do. Hi-ho, negative di-do. We're trying to calculate what's the height of my image. So we multiply both sides by ho, multiply both sides by ho. Height of my image is going to be equal to a negative, the distance is a -6.0 centimeters. The height of the object is 2.0 centimeters. The distance of the object is 2.0 centimeters. Those cancel, the negatives cancel. The height of my image should be at 6.0 centimeters. And that's very close to the 5.7 that I measured on my graph. That's it. That is convex lenses, and we will not be doing concave lenses.